If you haven't downloaded the free software you need for this lesson already, then please pause this video, go back to Canvas, go to the home page, watch this 1-minute set of instructions, and then go to this link to download the software you'll need. Once that's done and the software is operating correctly, then you can resume the Topic 3 lesson. Hello, math students. Topic 3 is on direction fields. For first-order ODEs, one can produce a direction field, or sometimes called the slope field, which indicates the directions of the functions in the general solution. Complete the table below and produce the beginning of a direction field by hand, then use technology to confirm and complete your direction field. Okay, so what we're looking at here is a first-order differential equation that's in normal form, meaning I have the y prime isolated. The other side over here could either have any mixture of the independent and the dependent variables. So sometimes we can call this, it's any function of both t and y, where t is the independent variable and y is our dependent variable. Now, another way of writing a derivative, of course, is using Leibniz notation. In this case, it would be dy dt. And if you recall, the derivative tells you the slope of the tangent line. Right, dy dt is a rate of change in y with respect to t, or change in y over change in t. So, if we are at a certain point somewhere in our plane, our yt plane, pick any point, and let's start with the point right here, 1, 2. All of our solutions to this differential equation will be y as a function of t. So we have the plane here ready to receive those solutions. And the point 1, 2, let's locate that, time 1, y2. So here's the point 1, 2. So there could be any number of solutions, right, that pass through that in theory. However, according to this differential equation, it's right here, if you plug in t equals 1 and y equals 2 into this side of the differential equation, you get a value. That value is the value for y prime, which tells you how steep, or the slope, I should say, what the slope is of the solution. So plug in 1 for t and 2 for y, and notice we get 0 back from this side of the expression, which tells us that y prime is 0. So whatever our solution is that's going through this point, we know that the slope of the tangent line, the slope of the solution, will be 0. So I do a little line through there like that has a slope of 0. So a solution would not pass through this point like this. That's not a possibility. The solution would have to do something like where we had a horizontal tangent line right there of slope 0. Or something else that flattens out at that point. But we know that the solution that goes through that point is going to have to flatten out at that location. And we can do this now all over the place. This entire grid over here could be just filled with little direction arrows that tell us the direction that the solutions are at the different points. So let's just by hand fill in the rest of this table. So at the point 3, 1, so 3, 1 is over here. Plug in t equals 3 and y equals 1 up here, and we get 6 minus 1, we get 5. So we know that, now to do a slope 5 means you would go over 1 up 5. So a line like this is a line that has a steepness of 5, a slope of 5, but I just want to do a little tiny segment of it through that point. So I'm going to crop that down. Try to keep the same steepness, but this is the how steep we expect our solutions to be for any solution that passes through 3, 1. It'll be that steep. Okay, next point, 0, 2. 0, 2 is right here. And plug in 0 and plug in 2 into this differential equation. t0, y2, we wind up getting -2 for y prime. So we expect our solution, any solution that's going to pass through 0, 2, to have a slope of -2. So I draw a little line segment that has slope -2, and then I'm going to just shrink it a little bit. And put a little arrow. Okay, next one. 0, -3. 0 goes in for t, -3 goes in for y, and we wind up getting +3 back for y prime. So at 0, -3, way down here, we need to draw a +3. So that would be a slope of a line with slope 3, right, over 1, up 3. But now I'm just going to shrink it a little bit. Okay. Continuing with this, -2, 1. -2 goes in for t, and 1 goes in for y. So we wind up getting -5 as a slope. -2, 1 is right here. And the slope would be -5. So that's over 1, down 5. So it takes me right there. So I'm going to draw that line first. I'm going to erase that stuff. So something like that. And finally, the last one in this particular table is at -1, -2. -1, -2 location is right there. Plugging in -1 for t and -2 for y, we wind up getting 0. So another location where we would expect solutions to be flat. Now we only have 6 points of data here. You could keep going. I left an extra blank row here for you to put in any point you want. Maybe let's do the point 21, see what happens. But you can put in any data you like here. Put in t is 2, y is 1, and that gives us a 3 for y prime. So 2, 1 is located right here, and we expect a slope of 3 at this one. 3 is not as steep as 5. So this line is a little bit less steep than that one was. But once they get very steep, it gets hard to tell with the naked eye, right, just how steep these things are. Move that down slightly and then shrink it a little bit. All right, now we're going to learn how to do this using technology. There was a previous video for downloading dfield.jar and getting it installed. Once you have that installed, go ahead and open the dfield.jar file. We can close that. We don't need these messages. These are the two fields that I'm interested in. Now to enter a differential equation into this, notice there's a tiny little prime right here. It's very tiny, but it's definitely there. And to match our notation, we want to have y be the dependent variable. So I'm going to change that to y. You can effectively ignore the instructions here that say you have to write it in the form of x prime equals f of tx. You can really use any letters you want for the dependent and independent variables. So whatever you put here with the prime will be the dependent variable. And then over here, type in our 2t minus y. Now here you do want to make sure that your independent variable is the correct one. So if this was an x there, then you would not want a t up in here. You would want to put an x. So make sure that those match. Your independent variable is the t, and the dependent is whatever you put in the prime box. These parameter expressions, you don't need to worry about messing with that. That's in case you wanted to put like an a up here and then simply change a to different values and see how that affects your differential equation, but let's leave the parameters out. Our display window, I'm going to do a display window from -3 to 3 for the t's, and for the y's also -3 to 3. And then you hit graph phase plane. And over here you see our direction field that was created. Here they're calling it a phase plane as well, but direction field is what we'll call it, or a slope field. And this has all those little arrows that show you the flow of different solutions. Now remember, differential equations have multiple solutions depending on the given conditions, depending on what point you want your solution to pass through. Okay, moving on to the next slide. We're going to get a solution, a general solution to this differential equation. And in order to do that, I'm going to open up wolframalpha.com. And I'm going to type in solve, and then I'll type in the differential equation as I see it here. Y prime is equal to 2t minus y. Before I hit enter, we will later learn in this class very shortly how to solve this by hand, but right now we're just getting a solution using technology. So I'll hit enter and see what Wolfram Alpha produces for us. Okay, right here under result, it says y of t is equal to, well, first of all, under solve, make sure it got interpreted correctly. This says y prime of t is equal to 2t minus y of t. So it's just being formal with the function notation, showing that y is a function of t. Y is a function of t. So this is it. This is y prime equals 2t minus y. It's interpreted correctly. The independent variable is t. And then our result is the solution. This y of t equals c1 e to the negative t plus 2t minus 2. Now the c1 is the arbitrary constant. So back to our notes, I'm going to write down our general solution. It's y is equal to arbitrary constant. I'll just put a c instead of c1. E to the negative t plus 2t minus 2. Okay, now we're going to do this step of the instructions. Verify that the general solution satisfies the ODE. Okay, so we're going to find the derivative of this function now using our rules for derivatives. Y prime is equal to the derivative of c e to the negative t will be, the c will stay, and the chain rule will put a derivative of negative t in front of all this, which is negative 1. So negative 1 times c, and then e to the negative t, plus the derivative of 2t is just 2, and the derivative of negative 2 goes to 0. So now what I'm going to do is substitute this expression right here, goes in for the y, any y's you see in the differential equation, and then this expression here goes in for the y prime. I'm going to rewrite this and see if in fact we get the same thing. You can do this a variety of ways too. You could just plug in and just make sure that both sides wind up being the same, or you can just do this side of the equation only and see that it winds up being the same thing as y prime, which we have right there. Let's do that. I'm going to just copy this part right here. So I'm going to say 2t minus y, which is the same thing as 2t minus, and then replace y with this expression. So I'll just copy it, paste it there. So there's the y. Okay, so here's where we're at. We distribute this negative sign across. So we have 2t minus c e to the negative t minus 2t plus 2. Notice the 2t's cancel each other, so we just get minus c e to the negative t plus 2. And notice that's the exact same thing as y prime. Let me do this. So we've confirmed that the differential equation, the general solution, is in fact a solution to this differential equation. So we check. Now we're going to do by hand, following the instructions. It says, find the indicated particular solutions by hand and use technology to graph them over the direction field. So I've already imported the direction field here into our notes. This is the one we just produced using the dfield.jar program. For the first particular solution, we want our solution to go through the point 0, 2. Y of 0 will be 2. So it's tricky to track the axes down here. Let me go ahead and put them in a little bit more obvious. So there's the horizontal axis, the t-axis, and here's the vertical axis, the y-axis. And 0, 2 is a point on this curve. Now looking back at our previous, we saw that at 0, 2, we expect the solutions to have a slope of -2, which is what you're seeing with these direction arrows. We expect our solution to, oops, that's the erase button. We expect our solution to be passing through that point, something like this, whatever our solution is that goes through 0, 2. Now we want to find the value of C that goes through, so that the general solution will go through this point. So I'm going to take this general solution, copy that down here, and we plug in 0 at the same for t at the same time we change y to 2. So we're going to get a c times e to the 0. That's just going to be a c. Plus 2 times 0, that's gone, and then minus 2, and then add 2 to the other side, and we get 4 is equal to c. Therefore, our particular solution is y is equal to 4e to the negative t plus 2t minus 2. And this is the solution that goes through the point 0, 2. Now, it can be graphed multiple ways. I'm going to graph it using Desmos. So typing in y is equal to 4e to the negative t. For Desmos, we'll recognize t or x as an independent variable, so there's some freedom there. Plus 2t minus 2. And this is what that particular function looks like. In our direction field, this doesn't have to be perfect by hand when you're doing this by hand, but this solution follows these arrows, if you will. It does something like this. Okay, let's find another particular solution. This time we want our y of -2 to be 1. So we want to go through the point -2, 1. We're going to go left 2, up 1. So we're going to be passing through this point right here. If you remember from our direction field up above, -2, 1, we did do that data point. -5 is the slope I expect. So I could just copy this here and bring it down here. And at -2, 1. That's the steepness of the line of the curve we want going through that point. Notice it just follows those direction arrows. Okay, now let's go ahead and find the value C that's needed. So I'll copy this part here again, bring that down. This time we plug in -2 for t at the same time I plug in 1 for y. So we get C times e to the 2 plus 4 minus 2. And 4 minus 2 is 2, subtract it to the other side, and then divide by e squared. And I get 1 minus 2 is -1, divide by e squared, and this is my value of C. So the particular solution this time is y is equal to -1 over e squared times e to the negative t plus 2t minus 2. I'm going to type that one in to Desmos next. Y is equal to -1 over e squared times e raised to the negative t plus 2t and then minus 2. And clearly you can see that we've done something wrong. And now I'm seeing exactly what it is. Let's go back here and correct this. I did not plug in -2 correctly right here. That should have been a -4. So if you saw that error before I did, congratulations. So that winds up being a -6 on that side. Add it to the other side gives us a 7. So this should be a positive 7 over e squared. Let's get this corrected. Back up to here. Get rid of that minus sign. Positive 7. There we go. There's the solution that we were after. I knew my other one was wrong because it didn't even go through the correct point right there, -2, -1. We knew our solution had to pass through that point. This one dips below, and I won't do this entirely accurately, but it'll be good enough. So our solution comes down, it dips below the x-axis, just kind of follow the arrows, if you will. And it goes up like that. So there's our second particular solution. Now, in Desmos, if I were to, I'm going to copy one of these and change this coefficient in front to a capital C and then add a slider for capital C. Now I want to show you what what this allows us to do. This shows us all possible solutions. Let me change the color. As you do different possible coefficients for C. And it gives you the family of solutions that are different possible solutions for this differential equation, depending on what point we need the solution to pass through. And you can also just hit play and let this cycle itself forwards and backwards. And all of these green curves that you're seeing are curves that are going with the flow, if you will, when you put this over the direction field. In fact, let me go back now to our dfield.jar software and show you how you can plot specific solutions in this graph as well. So click on solution right here and say keyboard input of initial value. This brings up another window. Let's bring that down here. And you can put in your initial conditions, the point, in other words, the point you want your solution to go through. So looking back at our notes, the first particular solution we got was y of 0 is equal to 2. So t was 0, y was 2, and then you can say solve, and it puts that image, that solution in there for us. If ever you want to delete one of these, the way I know to do it is just say, go back up to here and hit graph phase plane, and it sort of refreshes the phase plane. You can put that back in there. You can also specify an interval. We'll do that here in a moment. Let me now put in the other initial condition, which was t was -2 and y was 1, and then say solve. And it puts in that second particular solution for us. Let me erase those by hitting this button. You can also specify that I only want to see the solution for -2 and on. Notice it stopped here. It looks like maybe we should put an ending value there and then say solve. Okay, so now this is only showing you the solution from t equals -2 and on. So here is t equals -2. I had a y coordinate of 1, and then here's what the solution did as t moved forward. You can crop it from... Now this one, the previous graph is still up there, so you may have to say graph, erase this, and then say solve again. And there we go. So at t equals 1, you can see our curve stops. It's only showing us the solution from -2 to 1. So here's a way that you can crop solutions if that's what you want to do. Sometimes solutions only exist for certain values of t, and so we just want to see the solution for those values of t. Let me undo that, clear the graph there, say solve again. And you'll notice it graphed this direction first, and then later it graphed back that direction for other t's. I don't know if you saw that. It happens very very quickly. Okay, here's another thing you can do. You can click anywhere in here, and it's going to make a solution going through that point. So the clicking is a little bit harder to control because you're not always exactly at the point you need to be at, but let's try to click at -2, 1. So I'm going to go to, here's -2, this line here, and to 1. So roughly in here, if you double click right here, it'll make that graph. And so you can actually start just double clicking all over the place. And you get a sense for what the whole family of solutions look like. Click over here. Looks like a single click too. You don't even need a double click. Just go crazy. And you get to see all at the same time a whole bunch of members of this family of solutions. You will notice a couple things that are of interest. No solutions cross each other, meaning that if you need your solution to go through a particular point, there will only be one possible solution going through that point. This is an interesting phenomenon. Right? No solutions cross each other. And of course, there's some underlying math theory for why that is, about uniqueness of solutions. Like if you want a solution to go through a certain point, you're not going to get multiple graphs that are possible solutions. It's not always the case that solutions are unique, but there are math theories been developed to determine the kinds of differential equations that will produce unique solutions that go through certain points. Now, this is all of these together is the general solution, and then the particular solutions are any one of these. Okay, let's go back to our notes here and go to the next page. There is another strategy for producing direction fields. An isocline is a set of all points for which y prime is constant. Find the indicated isoclines for the ODE below. So it's the same differential equation that we're working with, and we're going to, by hand, produce the beginnings of a direction field. All right, so here's where you predetermine what you want y prime to be. So instead of plugging numbers in for t and y and seeing what y prime is, which is what we did before, you say, what if I want y prime to be a specific thing, and then I want to figure out all the points where that's true. So for example, if I say y prime is 2, then you simply change y prime to 2, and then you solve this, oops, that should be a minus sign, not an equal sign. Then you solve this, I'm going to solve it for y. So I'm going to add y to the other side, subtract 2 back to the, also to the other side. So you get y is equal to 2t minus 2. So if you go back over here and you graph that, y equals 2t minus 2. 2t minus 2 is a line of slope 2, something like this. And it goes through negative 2. Oops. Try to make that look somewhat accurate. Good enough. So this line here, and let me go ahead and make it dash. It's not a solution to the differential equation. Well, what it is, oops, I want to do this style, let's make it dashed. What it is, it's the set of all points for which the slope of the tangent line of a solution will be this number here, 2. So every single point along this diagonal line, we expect to see a, it's interesting that this diagonal line also has a slope 2, but we expect, if you're to pick any point along here, we expect the solution to the differential equation to have this slope as well. I pick any point on this diagonal line, the solution will have a slope that is 2, which happens to be the slope of the diagonal line itself. That's not always the case. Right? If you look back at our image, let me draw this, let me copy this isocline and put it back into the image of the context of our, there we go. We want the slope, there we go, that looks about right. All of your solutions have slope negative 2. Sorry, slope 2. Notice that all the little arrows, which raises an interesting question. Returning to our direction field, and clear all that. If we started at 0, negative 2, since it feels like, let's see what happens here with the slope, or the solution. When we start on this particular isocline, because the slopes stay 2, and you're already on a line of slope 2, and every single point along that line preserves that slope 2 according to the isocline, then our solution will simply be a line in that case. In other words, we should wind up getting C to be 0. All right, I leave that to you to verify. Do a particular solution that goes through 0, negative 2, similar to what we did up here, and you will notice that the C needs to be 0 in that case, meaning that your solution simply is the line 2t minus 2. Okay, let's do the next isocline. Isocline of y prime being 1. So change the y prime to a 1 in our differential equation and solve for y. And we get y equals 2t minus 1. Well, that's going to be an isocline that's also a line slope 2, but it goes through negative 1 on the y-axis. So let me move this down. So it's this isocline right there. And every single point on this line here, on this isocline, is going to be, the solution will pass through that line with slope 1, which is different than the slope of the isocline itself. So our solutions will pass through this line. We're going to expect to see slope 1. Any solution going through this line will pass through it with a slope of 1, etc. Which means that your solution won't stay on that line. Okay, let me copy this isocline back up to this image. There we go. Okay, now notice that what's happening here, as solutions pass through this dotted line, they do so at a steepness of 1. So right here, oops, didn't mean to move that. As we go through, as this solution goes through that line, it does so at a slope of 1. Every single solution you could possibly draw is going to cross that line, even right here. Oops, did not want to do that. It's going to pass through the line at a slope 1. Erase too much. There we go. So this is simply a way just to get a whole bunch of arrows quickly. It's faster than what we did up here. Here we just had to do one arrow at a time, one calculation at a time. Here we get a whole bunch of arrows for effectively doing one calculation. Let's do a few more isoclines. When y prime is 0, plug in 0 for y prime. This leaves negative or 2t minus y. Solve for y, we just get y equals 2t. So that's this same isocline, except it's now going through the origin. So here's our isocline there. And every single point on this isocline, the solution that goes through that isocline will do so horizontally. So you get a whole bunch of, get all these horizontal transitions through this isocline. Copy that and move it up to this image. Notice how every single green little direction arrow flattens out as it goes through that line. Back in this image, here was that isocline. Notice we did find 2 points sort of randomly. We found this point here, and we found out that the y prime would be 0 at that point. And at this point down here, we also determined that the y prime would be 0, but both those points are on this isocline. So it doesn't surprise us. Now the next isocline, let y prime be -1. -1 is equal to 2t minus y. Add the y, add the 1, so y is equal to 2t plus 1. Let's just do this last one here really quickly too. -2 is equal to 2t minus y. Add the y, add the 2. So here's 2 more isoclines. Let's get them put in our image. Copy, paste. Grab that, there we go. So here's the one that's going, slope 2 going through 1. And let's paste one more. Here's the one that's slope 2 going through 2. And let's do this isocline first. We have -1 slopes as we go every single point on this line here. We're going to get a -1 slope going through it. So a whole bunch of these -1 slopes passing through this isocline, etc., all the way down, -1 slopes. And then the other one was -2 slopes. It's a little bit steeper. Obviously doing this by hand is not ideal. That's why we have the software to do it for us, but I just want you to know what the software is doing for us. And this method of isoclines is a fast way to get a whole bunch of arrows. Okay, we've already used technology, reading this part here, we've already used the technology to complete the direction field. It's the same direction field that we have right there. And let's move on to the next and final slide here. Complete the tables below and produce the beginning of a direction field by hand for the given ODE. So we have a new ODE finally, so we have a new example. S is clearly the dependent variable, and look over here, I don't see another variable at play. This is a case where the independent variable is not explicitly mentioned. in general, when you have a first order differential equation, you can isolate the y prime and get the other side to be a function of both the independent and dependent variable. And be flexible with what letters we use here. But in some cases, that the other side does not depend on the independent variable explicitly. It just depends on the dependent variable. So in other words, there's no independent variables over there. This is a case where we say that the differential equation is autonomous. It's not a word I'm going to test you on, but I just want that thrown out there in case you read it somewhere. This is an autonomous differential equation. It does not depend on the independent variable, which is exactly what's happening here. Like, there's no other variable present. This s prime is simply a function of, if I write it this way, it's a function of s only. I don't see another variable here. So when I'm doing the old school way of plugging in or picking any random point in here, let's pick the point 1, 1 for example, or 2, 1, so they're different. Well, x is 2 and s is 1. So it doesn't really matter. I'm going to be doing this one here first. It doesn't really matter what x you pick, because s prime doesn't depend on on x, right? It only depends on s. So it just matters what the s coordinate of that point was. And when you plug in s equals 1, plug in s equals 1 here, notice you get s prime will wind up being 0. And this is true no matter what x coordinate you picked. So in other words, you're going to get a horizontal arrow here everywhere along this horizontal line, because it doesn't matter what x is, it just matters that what s is. So it seems like kind of like we found an isocline. We found a set of points where the s prime is going to be the same thing always. Let's go back up to here. Pick any point that has a x coordinate, whatever, and as long as the s coordinate is 2. So here's -1, 2. Plug that into the differential equation. Again, it doesn't matter what x was, just that s is 2. We do 1 minus 2 squared. 1 minus 4 is -3. And so we get -3 here. So we get a -3 slope on a very steep slope like this. And this is going to be true as long as if you pick any point that has an s coordinate of 2. So it seems like we found an isocline. Now let's do 0.5 for s. It doesn't matter what x is. Plug in 0.5 for s. Square 0.5, that's going to be 1/4, and 1 minus 1/4 is 3/4. So s prime will be 3/4. And so everywhere along the line y equals, or s equals 1/2, which is this line right here, we expect a slope of 3/4. So not quite 1. Etc. Now when s is 0, plug 0 in for the s up here, and we get 1 for s prime. So we get slopes of 1 as long as s is 0, so a little bit steeper than the ones I just drew. But slope 1 all the way through there, etc. When s is -1, looks like we plug -1 in for s here, and we get 0 for s prime. So everywhere along this horizontal line, we also have these 0 sloped line segments. And finally, let's do one more. When s is -2, square -2 is 4, 1 minus that, we get -3 again. So I can effectively copy all those and paste them right somewhere along that -2 horizontal line. Okay, so we have the beginnings of a direction field that we've done by hand. If we take the isocline route, and I predetermine what I want s prime to be, let's do this isocline 1 here, because I've already seen where an s prime is 1. We simply change s prime to 1 in our differential equation. So we have 1 equals 1 minus s squared, and then we solve for s. So we get s squared is equal to 0, so s is equal to 0. So s is equal to 0 is the horizontal line at which s prime will always be 1. And we've already sort of determined that. That line right there, s is equal to 0. All the s primes will be 1. Let's do s prime to be 2. So we get 2 is equal to 1 minus s squared. So s squared could be, well, notice we have a problem here. This would suggest s squared is equal to negative 1. So no solution. In other words, there's never going to be a solution that has a slope of 2 in this particular differential equation. We'll examine that here in a moment with technology. Let's do the 0 for s prime. So 0 is equal to 1 minus s squared. Solve for s. S squared has to be 1. So s could be plus or minus 1. So that's two different heights. And we found that. When s is 1, the slopes were 0. When s was negative 1, the slopes were 0. So notice in this particular case, it feels like either method, just picking random points, but then realizing that the x-coordinate can be anything. That doesn't matter what those are. It felt like we were already finding isoclines. And here, when we find finding the isoclines specifically, we are just sort of reconfirming data we already found using the other method. Let's just do this last one here. S prime is negative 3, so we have negative 3 is equal to, plug negative 3 right there and then write that part, is equal to 1 minus s squared. Solve for s squared. S squared has to be 4 for this to happen, which tells us that if s is 2 or negative 2, then the s primes will be negative 3, which is something we already discovered, right? When s was 2, the s primes were negative 3, and when s was negative 2, the s primes were negative 3. Okay, I'm going to go back now to our D field. I'm going to erase that, the image we had there, come back up to here. We want this to be s prime now. We want this to be 1 minus s caret squared. Independent variable could be t. It doesn't really matter what it is. I can put an x there and it won't matter. Or t. You can. I think in our notes it's an x, so I'm going to make this an x as well. And how do I know that from the notes? Because I put x coordinate there and I put an x coordinate down there. Let's keep the same window from negative 3 to 3, negative 3 to 3, and graph the phase plane. Okay, so here's what we're seeing. We definitely can see the two horizontal bands, if you will, at 1 and negative 1. Let's do some initial conditions. I know this says, let's cancel this and try this again, see if it comes up with s's and x's. Oh, it does, okay. So maybe you have to do that, because before it said t's and y's. I'm not sure if it would connect, but I canceled it and then redid it. Okay, so let's start off a solution that has an s coordinate of positive 2. So x equals 0, s is positive 2, and say solve. So there's our solution. It's a solution that's decreasing and appears to be following a horizontal asymptote at y equals, or s equals 1. What would happen if we started on that asymptote, 0, 1, and say solve? Notice we get that horizontal line. So any solution that starts on that horizontal line is going to stay on it. And the solution, the particular solution, will be that horizontal line. Same thing is going to be true if I start on the other horizontal line. So any solution that passes through a point on that horizontal line, that solution will be that horizontal line. If I start with an s coordinate somewhere in between negative 1 and 1, like at negative 0.5, for example, notice our solution looks like a arctangent graph, right? It has a horizontal asymptote, it climbs up to the other height, and then has a horizontal asymptote, kind of like an airplane taking off. And if I start with something below the horizontal line of negative 1, like at negative 2, and say solve, we're going to get a graph that pulls away and goes down forever as you go to the right. Of course, it has an asymptote on that side. And now let's just go crazy. Let's just start clicking all over the place and seeing all the different possible particular solutions and what their behaviors look like. Now remember, we discovered a moment ago that when I tried to find the first isocline when S prime was 2, that we discovered that there was no solution, meaning that there is no solution ever that's going to have a slope of 2. And if you're looking at this, you can see why. All the solutions that are above s equals 1 have only negative slopes. All the solutions that are below -1, s equals -1, also have negative slopes. And the only ones that have positive slopes are up here in between. But they never get steeper than 1. In fact, S prime, the largest S prime can ever be given this particular differential equation is 1. And that steepness of 1 happens when S is 0, right through here. So all these points and all these, if you look just along this horizontal, these are all the steepest points that any solution, at least in the positive slope direction, are ever going to get. These are the highest slopes possible. Of course, you do have a lot steeper stuff, but it's in the negative direction in these other locations. So in the positive direction, as far as going up, we're never going to get steeper than a slope of 1. And that happens for all these solutions right along this horizontal line.